So measuring heat which comes out of a reaction or the heat energy we have to put into a reaction is not only a kind of interesting, useful thing, it connects to something very fundamental, right? The energies of electrons in bonds. So it's really useful. In a previous section of the course, we described a very simple apparatus for measuring the enthalpy of a combustion reaction. In fact, specifically the example of octane. Now we need to do a better measurement of that, right? We need a better measurement of heat transfer than the one we talked about earlier. So we need to understand a new process. This process is called calorimetry. So calorimetry is the experimental technique associated with measuring heat coming in and out of chemical reactions. And the device we do calorimetry in is something called a calorimeter. And there are lots of different kinds of calorimeters, and we won't bore you with all the different kinds. We're going to talk about two very simple ones. The first is, the most easiest to understand, is what's called a constant pressure calorimeter. And that's directly connected to enthalpy, because remember, enthalpy measurements are made directly at constant pressure. So if we do the calorimetry at constant pressure, then that heat connects directly to enthalpies of reactions. So before we get to combustion, let's talk about a different kind of reaction first, and then eventually we're going to come back to combustion. Let's talk about the decomposition of hydrogen peroxide. Hydrogen peroxide undergoes a chemical reaction. Let's draw the chemical equation. In fact, let's draw hydrogen peroxide as a Lewis structure in our chemical equation. There it is. So it's 2 oxygens and 2 hydrogens. This is hydrogen peroxide, H2O2. And when it reacts, it will react to give water. So here's our water, right? And it also makes oxygen, molecular oxygen. So we'll draw a Lewis structure for oxygen that way. And if we want to balance the equation, we need 2 moles of peroxide, 2 moles of water. So hydrogen peroxide is what's called a monopropellant. That's something which will generate gas without having to be burned, without having to add anything else. So it just does it all on its own. So this is used actually for maneuvering, spacecrafts and anything with very, very small engines. And so presumably this reaction is going to go. Presumably it's exothermic. How do we actually measure how exothermic it is? Well, it needs a catalyst. We're going to talk more about catalysts later. For now, let's just accept the fact that the catalyst is going to help the reaction go. It doesn't change the reactants of the products. It doesn't change the reaction enthalpy. It just affects the path, right? And remember, reaction enthalpy is a state function and so on. So you can do this in an apparatus which is, quite frankly, is only a little bit more sophisticated than what we learned about earlier. This thing's called a coffee cup calorimeter. Here we go. And so you actually use an actual coffee cup. Coffee cups are fairly well insulated. It's insulated. They're made of polystyrene. And just like we don't do too many drastic things like large amounts of heat coming in and out, this is really for measuring heat coming out. Then we can measure heat coming out, fairly easy, just with a coffee cup. So we'll have a coffee cup. We'll have some kind of, insulated lid on top of the coffee cup. Oops, insulated lid. Right there, we'll have a thermometer. And we should have some way of stirring what's inside to make sure everything's mixed up properly. And then we'll have a sample solution right there, sample solution. And you'll notice we're doing this in solution. So if it's in solution, there's no work, and the pressure is basically going to be the same. And so if work is 0, then then the heat coming out of this apparatus is going to directly connect to enthalpy, which is exactly what we want to do. And so again, if the reaction is exothermic, then the temperature of the water will increase. We'll be able to measure that on the thermometer, and then we'll be able to calculate reaction enthalpy. However, there's still something missing, because what we're actually going to measure is temperature, and what we want is enthalpy, which is an energy. So we need to go back a little bit to our discussion of the connection between temperature and energy. In fact, really, we need to understand a new concept. A concept of heat capacity and specific heat capacity. we have to worry about this now. We didn't before, because before we talked about the connection between temperature and energy. That was for an ideal gas. Well, we're not talking about ideal gases anymore. We're talking about real materials. In fact, in this case, mainly we're talking about water. So, here is the water, the H2O. That's where the energy is going to go. That's what we're measuring the temperature of. And liquid water is not an ideal gas. So it turns out we need to return and revisit this idea, this connection between temperature and energy one more time. And to do this, we need to talk about this new concept of heat capacity. So heat capacity for a while, then we'll come back and talk about calorimetry and how we'll actually do this experiment. But first, a diversion to heat capacity.